In order to complete this single leg hip thrust, my body needs ATP. I can either get ATP through an anaerobic pathway or an aerobic pathway. When we're going through aerobic pathways, this means we're either getting ATP through the Krebs cycle or ETC, and if we're getting energy from an anaerobic pathway, this means that we are either using PCR or we are using glycolysis. While performing this back squat, I am burning carbohydrates. Our muscle cells store glycogen in them as an energy source. While we are performing exercise, our muscle cells break down the glycogen into glucose. This glucose is then used as a source of energy for contraction. ATP is split into ADP and inorganic phosphate. This provides energy for a muscular contraction. This immediate increase in ADP concentrations stimulates creatine kinase to trigger the breakdown of the phosphocreatine system to resynthesize ATP. If exercise is continued, glycolysis is initiated, and finally aerobic metabolism begins to produce adequate ATP to meet the energy needs. RER is known as our respiratory exchange ratio and is the ratio of carbon dioxide produced to the oxygen consumed. When we are burning carbs, we are closer to an RER of 1, and when we are burning fats, we are closer to a 0.7. Whenever we are working out, we are using Heinemann's principle. At first, we recruit our slow twitch fibers, which are responsible for our posture, and then we recruit our fast twitch fibers, which are responsible for forceful contractions. In the concentric movement, I am recruiting more muscle fibers, and in the eccentric movement, I am recruiting less fibers to lower the weight back to the ground. During exercise, our body produces lactate. This lactate is then transported to the liver through our blood and is used to convert the lactate into glucose via glucogenesis. This new glucose is now released back into the bloodstream and transported into the skeletal muscles, where it can re-enter the Krebs cycle. Lactate typically forms during intense exercise because we are unable to break down the NADH quick enough through the electron transport chain. While performing these leg extensions, my skeletal muscle is receiving an excitatory postsynaptic response. This causes my muscles to contract and allows me to move the weight. Curls, a depolarization is occurring in the muscle cell. A depolarization occurs when sodium floods the cell, bringing the resting membrane potential to 55. Once it occurs at 55, a depolarization is sent through the axon into the dendrites where the muscle signal is received. At positive 40, the sodium gates close and potassium gates open. This is now a repolarization that occurs, and this will go into a hyperpolarization, which is then fixed by the sodium-potassium pump to restore the inside of the cell back to its resting membrane potential. While performing these dumbbell pullovers, my Golgi tendon organs are detecting the tension within my muscles, which acts as an aid to allow my muscles to stop to prevent me from injuring myself. During exercise, we switch from our parasympathetic nervous system to our sympathetic nervous system. Our sympathetic nervous system regulates the blood flow towards our working muscles. Once we are done with exercise, our sympathetic nervous system slowly decreases and our parasympathetic nervous system increases. While performing these bent over rows, I am switching from a parasympathetic state to a sympathetic state. While I'm performing this exercise, I am using my acceleratory nerve in order to increase epinephrine and norepinephrine into my system. When I have norepinephrine and epinephrine, I'm able to put high power outputs and work out on demand. While working out, our heart has electrical signals that are sent through it. These electrical signals start at the SA node, and then through intercalculated disc, they go to the AV node. At the AV node, it reaches the bundle of His, goes down the bundle branches into the Purkinje fibers, where the left ventricle is then depolarized and we're able to have blood come out of the aorta. While performing the leg extensions, my muscles are accumulating acid. This acid could either come from lactate, this can come from CO2, or it can come from the breakdown of ATP. Whenever we are working out, there is a right shift in the oxyhemoglobin dissociation curve. This rate shift is due to an increase of pH, temperature, or CO2. Our working muscles are producing hydrogen ions, so in order to oxygenate those muscles and get rid of the waste products, we need that right shift of the oxyhemoglobin curve. Histidine dipeptides are the first line of defense when it comes to muscle fatigue. These are the sacrificial lamb proteins that denature before our muscle proteins are harmed and denatured due to the increase in acidity. While working out, our respiratory rate is going to increase. This is because we're trying to get rid of the CO2 buildup in our body. Our intrapleural pressure is going to decrease during inhalation due to the diaphragm contracting. This is going to do the exact opposite whenever we are exhaling the CO2. So yesterday I ran a 5K, so this does increase my work rate, this does increase my exercise rate, and while I was doing that 5K, growth hormone was being released, and this was being released from the anterior pituitary gland. Growth hormone is responsible for the uptake of amino acids and protein, and it increases lipolysis in the face of decreasing blood glucose. So I was burning glucose whenever I was going through my 5K, so in order to replenish that energy storage and so I can continue running, growth hormone kept on developing and kept being present in my blood. Whenever we manipulate our stroke volume, this has an effect on our cardiac output. So stroke volume can be broken down into preload, contractility, and afterload. During preload, it's greater the stretch, greater the squeeze. If we increase the preload, we increase stroke volume, which increases cardiac output. Contractility, if we increase contractility, we're going to increase stroke volume and increase cardiac output. But afterload is going to be the back pressure coming off the aorta valve. If we increase the amount of back pressure we have, we're actually going to decrease the stroke volume, thus resulting in there to be a decrease in our cardiac output. When we are exercising, we're actually increasing the acidity inside of our muscle. So we want to get rid of that acidity so we do not denature our muscle proteins. We have 3 ways to buffer out that acid. One way is going to be through the NHE transporter, which is going to have 1 sodium come in and a hydrogen come out. We also have the MCT transporter. This is going to allow lactate and hydrogen to come out of the muscle cell and into the blood. And then we have the sodium bicarbonate co-transporter. This one brings sodium and bicarbonate into the cell, thus increasing the pH. The bicarbonate buffer system is going to be the main buffer used in the extracellular system. In here, CO2 is going to leave the muscle and go into the blood. It will then hop onto a red blood cell and it will bind with water. That CO2 and water are going to create carbonic acid. That carbonic acid is going to dissociate on the red blood cell, leaving hydrogen on the red blood cell, but bicarbonate will hop off of the red blood cell. That bicarbonate is just going to chill out in our system until needed later. The hydrogen will then denature that hemoglobin, which allows oxygen to offload at our working muscles. Whenever we need to get that CO2 out of our system, that bicarbonate is then going to jump back onto the red blood cell, bind with hydrogen, make carbonic acid, and it will dissociate into water and carbon dioxide, which we then exhale. Whenever our heart contracts, there's actually an electrical stimulation that is sent throughout our heart. This is known as the cardiac cycle. First, the SA node is going to fire. This creates the P wave, which is going to be atrial depolarization. That signal reaches the AV node, and this is going to lead into a QRS complex. That is going to be ventricular depolarization and atrial repolarization. After that occurs, we have a T wave that is present on an EKG, and that is going to be ventricular repolarization. This is going to keep continuing every time our heart beats. To ensure that we get the proper blood flow to our working muscles, we are going to have vasodilation occur at our working muscles. We are also going to have vasoconstriction occur at our non-working muscles. We want that vasodilation to occur at the working muscles so we are able to offload that oxygen in areas that need it the most. Vasoconstriction occurs at areas that aren't working because they don't need that oxygen replenished. There are a few adaptations that occur whenever we resistance train. One of those is going to be neural tuning due to the motor sequencing that's occurring. Another one's going to be hypertrophy, and this is adding parallel series of sarcomere in the Z or the Y plane. This way we can produce the same force but with less effort. And then something that's not common in humans is hyperplasia, which is the increase of muscle cells. Whenever we're trying to build muscle, we need to stimulate mTOR. mTOR is what stimulates protein synthesis. So whenever we are going through protein synthesis, we are trying to build muscle. This can be activated through exercise, diet, or mechanoreceptors in the sarcolemma. At our active tissues, we are producing CO2 whenever we are converting the pyruvate into acetyl-CoA. So CO2 is acidic in our muscles and we want to get rid of it. In order to do so, we have CO2 passively diffuse into our bloodstream. And once it's in our bloodstream, it will bind with water on a red blood cell and it will make carbonic acid. That carbonic acid is then going to dissociate into bicarbonate and hydrogen. The bicarbonate will pretty much stay in our bloodstream, but that hydrogen will then bind to hemoglobin. That way we're able to get rid of the waste from our muscle and put it in our bloodstream. So in order to take a breath, our diaphragm has to contract. The reason why it has to contract is because it needs to create the pressure in our chest cavity to be lower than the pressure that's outside of our body. The reason being is because of the pressure gradient. We want to go from an area of high pressure to an area of low pressure. This will allow air to flow into our lungs and allow us to inhale. Now, the exact opposite is going to be to exhale. To exhale, we need our diaphragm to relax to make that pressure in our chest cavity be greater than the pressure on the outside. At elevation, we are actually going to have a decrease in the pressure of oxygen. This means that there's going to be a decrease in the pressure gradient between our internal environment and the external environment. This means that we will start lower on the oxyhemoglobin dissociation curve. We will have a lower starting point, not because there's less oxygen in the air, but there's less of a pressure gradient, which means that we're not able to take in as much oxygen as we could at a lower elevation. For people who live in elevation, they probably will have a few adaptations. They'll have an increase in red blood cells. This is so the concentration will increase, which allows for more hemoglobin to on and offload oxygen, and it will also lead to an increase in plasma volume. This increase in plasma volume will also increase our stroke volume through Frank-Starling's mechanism. We're able to put more blood into the heart and into the circulatory system, which allows for more on and offloading of oxygen onto hemoglobin. The force we produce is directly related to the number of actin and myosin that we have. With resistance training, we can actually increase our muscle mass, which does increase the amount of actin and myosin that we have. This means that we are creating more muscle tension to produce the same force but with less effort. Resistance training is essential for making sure that we keep our bones healthy. Women will reach their peak bone mass between the ages of 25 and 30. With resistance training, it significantly increases our bone density. Thus, it does increase the bone strength we have and decreases the amount of fractures that may occur. During endurance exercise training, we have two really big things that occur, but we also have a few more. But these are the two big ones. So we have an increase in capillary density and we have an increase in the number of mitochondria. That increase in capillary density, it allows for a slower blood flow in the muscle and increased free fatty acid transporters. There's now going to be an increase in uptake of free fatty acids, so we're going to be increasing our free fatty acid utilization, and it's going to spare our plasma glucose. Another adaptation that occurs whenever we are endurance training is the increase in mitochondria. So the reason why this is so important is because it changes the muscle acid-base balance. Our muscles like to stay around a 7.4 during rest at a good blood pH. So with that increase in mitochondria, we can actually increase the ability to handle the NADH and increase the amount of lactate being produced. This is because we're able to run through our aerobic energy systems and not rely so much on our anaerobic energy systems. So you may wonder what happens when we start detraining. So what happens exactly when we stop training, when we take a few weeks off? Well, whenever we take a few weeks off, we can actually see a decrease in our muscle mass, but we can also see a decreased VO2 max, and this is due to the decreases in cardiac output, our stroke volume, and our oxygen extraction. We also see an increase in heart rate, and we start to see a shift from slow to fast fibers. Whenever we are resistance training, there's a few signaling events leading to muscle growth. One of these is going to be ribosomes, are the protein factories that link amino acids together. Another one is resistant training increases ribosomes, which precedes hypertrophy. Interestingly, hypertrophy doesn't seem to result from increasing the production of messenger RNA, rather increasing the efficiency of it. Whenever we are prescribing exercise, the dosage depends on their health and fitness goals. For someone who is switching from a completely sedentary lifestyle, they will see increasing benefits as they increase the amount of exercise. There is going to be a point where there will be maximum benefits before there's injury if we keep adding exercise to their prescription. Once we push past that maximum benefit, there is increasing harm that can be done to the body. Whenever someone is pushing themselves to the max, they are increasing their chances of injury. Whenever we are prescribing exercise, we can do this based on the FIT principle. The F stands for frequency, the I stands for intensity, T stands for time, and the second T stands for type. The dose that we prescribe people does vary based on who they are and their activity level.